Alright, so second law of thermodynamics. So in our last video, in our last video I told you that laws of thermodynamics, the first one talks about thermal equilibrium, second one entropy. The zeroth law talks about thermal equilibrium, first one talks about entropy, second one talks about entropy, the third one talks about zero entropy. So second law of thermodynamics. The second law of thermodynamics talks about entropy. So first, what's entropy? You need to know that entropy talks about the degree of disorderliness of a system. So the degree of disorderliness, or you say the measure of intrinsic let me not speak one. So but the measure of disorderliness of a system is known as entropy. That's the first part, the first definition you need to know. The second definition you need to know is that you need to know that entropy talks about the number of ways a system can be arranged. So number 3, entropy talks about how much energy a system does not have. Now that means that at maximum entropy, that person will be dead. If it's a living thing, that living thing will be dead. At maximum disorderliness, you are gone, finished. Now, so if you know this, what does the second law talk about? Now the second law is saying that for any spontaneous process, you need to know that if entropy is talking about disorderliness, that means in summary, it's talking about how spontaneous is this disorderliness. How much on its own can it happen? How much on its own can it happen? Will the reaction occur? That is what it's saying. Like if I spray perfume now, naturally it will start flowing on its own. But a situation whereby is a reversible reaction, it now means that it's talking about being at equilibrium. So entropy can either increase or is zero. Not zero, or is just at equilibrium. And we know that entropy cannot be zero. So that's what third law is saying. The third law, when we get there, is saying that entropy cannot be zero. So if that is the case, the second law is saying that for any spontaneous process, the entropy of the universe and the system increases. He's saying that for any spontaneous process, the entropy of the universe and the system increases. So you need to know this. A question can come and ask you, what is the entropy of the universe? A formula for change of entropy of the universe. This is it. So change in entropy of the universe is equals to change in entropy of the system plus change in entropy of the surrounding. So for any spontaneous process, the entropy of the system and surrounding increases. So let me use surrounding in place of universe. Of the surrounding and system increases. For any spontaneous process, the entropy of the surrounding and the system increases. So you need to know that entropy is represented with S. Delta S means that it's a state function, change in entropy. So it's represented with S, and the unit of entropy is Q over T. So Q here stands for heat absorbed and heat released all over temperature. This is T. And know it that if temperature is not given to you, you take it that T is equals to 25 degrees Celsius, which is the same thing as 25 plus 273, which is equals to 298 Kelvin. 298 Kelvin. So this is the standard temperature we make use of when it's not given. So, but in most cases, it's always given. So since you know this now, you need to know that this is temperature, this is heat. At heat absorbed and heat released. But at any point where they did not give you Q, they now give you maybe mass and latent heat of fusion. Entropy can be equals to mass times latent heat of fusion all over T. A situation where they give you specific heat capacity, this means mass, latent heat of formation or heat of fusion over temperature. Then we have situation where we have M, mass, we have specific heat capacity, then we have change in temperature all over T, temperature. So these are the formulas for entropy. But if a question say using equation state the second law of thermodynamics, this is what you are requested of. This is what is requested or expected of you. Just this. But these are formulas for entropy, so that in any case you know it. So spontaneous change is described as a change once started, it continues by itself towards equilibrium. Entropy is an important property in the second law of thermodynamics. Entropy describes the degree of disorderliness of a system and gives useful information whether a process or chemical reaction can occur or not. The second law of thermodynamics, you need to know that simply put, it means that in any spontaneous process, the total entropy of a system and its surrounding increases. So you need to know that this law simply implies that chemical or physical change cannot occur unless the entropy of the universe increases. So there is no change. You need to know that there is no change which occur that can cause the entropy of the universe to decrease. So it will be easy. That means it will be easy to say that changes that occur are ones that lead to an increasing randomness or of the universe. So that means that it is much possible for you to have from solid to liquid and from liquid to gas than for you to have from gas to liquid and then to solid. In fact, it is natural for you to have more natural for you to have for spontaneous change to tend from solid to liquid and then to gas, because gas molecules are more random than liquid molecules and liquid molecules are more random than solid molecules. So now that you know this, let's move to the third law of thermodynamics. So the third law I will impregnate you with knowledge. I will impregnate you academically. Oh yes, the law is good. Alright, third law of thermodynamics. So the third law of thermodynamics can simply be put this way. He said that at absolute zero temperature, that is 0 Kelvin, or you say minus 273 degrees Celsius. The entropy of a perfect crystal at absolute zero temperature, 0 Kelvin or minus 273 degrees C. You see, at absolute zero temperature, the entropy, God know that this is not my handwriting. Oh God. The entropy of a perfect crystal is 0. So first of all, what this law is trying to say is that there's nothing like a perfect crystal, or there's nothing like a perfect entropy. So we can never have zero, nothing like zero entropy. So we can never have zero temperature. It's obtainable, but it's not natural. So chemists can obtain that, but through forced means. So absolute temperature, zero temperature, not possible. Perfect crystal, not possible. So entropy cannot be zero. That is why a question that asks you to show the value of pure substance for change in enthalpy, that is delta H, is saying that yes, delta H for pure substance can be zero. Delta G gives free energy can be zero for pure substance at STP, but entropy can never be zero for pure substance at STP. There must be a value for it. So if you know that, it's very important. So if you know that the third law is saying that there can never be anything like entropy, that is the summary at zero. That is saying that there can never be zero entropy. That's the summary of the third law. So at absolute zero temperature, the entropy of a perfect crystal is zero. So if you know this, you need to know that there are formulas to note, because both delta H and delta G and delta S, when any situation where you are not giving Q, you're not giving T, or you're not giving U and the work, but you are giving something like maybe equations, and you are told to calculate enthalpy change or entropy change. Let's say for example I have H2 plus O2 equals to H2O. Then they come and give me that this is 12, this one is 6, this one is 7. All those things, they tell me this is the value of the delta H. This is not obtainable, it's not possible. I'm just guessing, using it to show you as example. They come and give me delta S, maybe 2, 20, 6, 8. First of all, I know that this cannot be any pure substance, any pure elements. The enthalpy is 0. So the only one they can give me value for, enthalpy can only have value for compounds. So when I have this kind of thing, they tell me find the change in delta H. All I need to do is to say sum of, that is first of all, change in delta H, change in enthalpy is going to be sum of heat on the product part minus sum of heat on the reactant. So in which case here now I have product is 12. But first of all, we have to balance it. I have 2 here. I have this one too. Let me put 2 here. So this becomes 2. Then put 2 here. This becomes 4. So that means that here is now hydrogen is 2. So I will now have for the products. This is the product. This is the product. So I will have 2 times 12. Then minus whatever I have here is 0, 0. So I have 2 into 0 plus 0. So this is how you calculate enthalpy change. Once you notice that they did not give you those normal values and they give you something like equation 30 to find, so that this becomes 24 minus 0 plus 0. 2 times 0 is 0. So this becomes 24. I definitely know that value of enthalpy from the table for water is not going to be 12, but we are just calculating to show you example. So a situation whereby I am not giving Q, not giving mass, not giving latent heat of fission or temperature change and the rest. I'm just giving an equation and giving blah 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 values for entropy. They tell me the entropy value from the table is this, is this, is this. All I need to do is to simply do change in entropy is equals to sum of entropy on the products minus sum of entropy on the reactants. So that, for example, using this simple example, our rough example, these are blah 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 values we are using to teach. So, but if you look at this is the product parts. Pure substance will always have value, but if for entropy, but if it gives free energy and entropy, it will have 0. So if I know this, let me now come. Product is having stoichiometric coefficient of 2. So it's having stoichiometric coefficient of 2. So 2 times 12 minus, on the reactant part I have hydrogen 2, and the value given to me is 20. The blah 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 values is 20. Then oxygen, the stoichiometric coefficient here is just 1. So 1, so plus 1 into 6. So that this becomes 24 minus 40 plus 6. 1 times 6 is 6. So this becomes 24 minus 46. Are you checking it out? So this is the same thing as saying if 20 leave here, I'm left with 46 and 4 remaining here. If that is 26 and 4, if 4 leaves 6, it becomes 22, and there's minus on the greater number, so this is minus 22. Now you need to know the values. Now for whenever it's entropy, you need to know the units. You need to know that the units of entropy is simply kilojoule per mole. Is simply kilojoule. Yes, entropy is simply kilojoule because it's heat, and heat is more or less a form of energy. It's kilojoule. But this particular one for entropy is going to be joule per Kelvin. If you remember, it's joule per Kelvin because of the fact that entropy is equals to Q over T, which means that this is that joule, and this is that T, which is for Kelvin. So it's joule per Kelvin. And in most cases, you know that this is the same as kilojoule per Kelvin. In most cases, you will be required to divide by 1000, divide joules by 1000 in order to take this. Divide kilojoule, 1 kilojoule, then by joule, so that in order to take this to kilojoule. The question will come. When we get to that, you will know. But you need to know that joules to kilojoules simply divide by 1000. How you do this video is you watch, you rewatch, they become a part of you. Now notice that the third law, second law, first law and zeroth law, we've treated it and we've gotten to the calculations, we've gotten it. Now notice that all of them are treating this, but they have never been a part where entropy, and temperature, we are bringing it together. Entropy talks about heat, entropy, disorderliness, temperature, hot to cold. So a situation where we are bringing it together is now what gives us what we call the Gibbs free energy. In our next class, we'll be treating Gibbs free energy called delta G, and it says that delta H, entropy change, is minus temperature and multiplying delta S, entropy. In our next class, we'll be treating this Gibbs free energy. This is a more convenient way of checking if a chemical reaction can occur. So Gibbs free energy is all about checking if reaction can occur. Is a more valuable means of checking if reaction can occur compared to entropy. It's better to use Gibbs free energy. So in our next class, we'll use that. So thank you very much, Academic Daddy. Subscribe, like, and share.